Welcome to Empowered Learning. This is the second video in the video series for using definite integrals to calculate moments and center of mass. And so in the first video, we kind of went over the basic theory about moments and how what we really wanted to do in the beginning was take a one-dimensional figure and say, hey, to keep this one-dimensional figure from rotating, we wanted to essentially have all the torques that were being introduced to the system by the weight of all the masses that were on that one-dimensional figure. We wanted to balance those things out so that there would be no rotation, which means that the sum of all the torques would have to equal zero. We also saw from that we could sort of extract out the gravity portion of that and just look at the moments itself and see that what we really need to focus on is balancing the moments of the system. And of course, a moment is singularly just the product of the mass of that particular system at a particular instance times an x value with respect to the origin, or how far that particular x value is from the origin of the object. Okay, and so we saw from that how we could essentially figure out our one-dimensional point where we would like to have our center of mass would just end up being the system moment divided by the system mass. And we were able to define the system moment and the system mass in terms of definite integrals, because of the fact that if we took a one-dimensional figure and we wanted to cut it up into n number of pieces and we wanted n to approach infinity, then whenever we start talking about having n approach infinity for so many pieces, and so many pieces of a thing, and then adding it up, by definition, that is what an integral or an infinite sum is. Okay. So now we're going to look at a two-dimensional figure where we're going to essentially look at a thin plate, and we're going to study the moments that are acting upon it, both about the x-axis and the y-axis. Okay, so we're going to have that discussion, and then from there we're going to leverage what we know about the one-dimensional figure and its formula for the system mass, formula for the center of mass, to be able to come up with formulas for the center of mass for a two-dimensional figure. Okay, so we're going to extend our concept of center of mass to 2D space here, and we consider having a finite collection of masses located in an XY plane. So that is what you see here. And what we're going to do is just single out just one single mass location. Okay, so we're going to do that just to make things easy. So if we were to be able to point out every single little mass location that looked like m sub I here, and we were able to add them all up, then of course our system mass would just be the sum of all those. Okay, and again, depending upon the location that we're at on this thin plate, that would let us know what that mass would be. Okay, now each separate mass within this mass m sub I has a moment about the x-axis, and we refer to that particular moment as m sub I times y sub I. And we also have a moment about the y-axis, which we refer to as m sub I times x sub I. And so I'm going to draw this for you so that you can get an idea of why we say this. Okay, so I'm going to switch colors again here. So for the moment m of y times y sub I. Okay, now just in general, if I'm talking about a moment here, I'm just going to go back to the one-dimensional figure for a second. If this is my origin here, and let's say my mass is right here, and this mass, of course, is going to have some weight on it. If gravity is acting down on this thing, then this particular system is going to tend to try to rotate like this. It's going to try to rotate clockwise, okay? Because of the fact that the force, which will be the weight of that mass, is actually trying to pull that rod down, okay? So in saying that, notice that we have the mass, and the force that's being applied is in a vertical motion, okay? And when that happens, we're going to have this thing spin. Now, if we take that same kind of thinking here, and we say, I have this mass, and let me, I'm going to put it in red here. I have this mass, and I have some force acting on it here in this vertical motion, okay? Then what we imagine here is that if it's going to act in this vertical motion here, then we are going to have rotation about the x-axis. So imagine that this force that's coming here is making this mass kind of spin in a direction of going out the page like it's coming towards you, okay? And if we imagine it like that, then we can kind of imagine this force kind of rotating around the x-axis, okay, with that mass sort of hanging on the end of it. And so that is what is meant visually when we say, when we have a mass with a moment m sub I has a moment about the x-axis of m sub I times y sub I. And of course, this length right here is a length of y sub I. It's just some y value. We don't know exactly how much it is because we haven't specified that, but we know that it is a y value, and that's the part that's important to us, okay? All right, so I'm going to try to draw that back there. Now, if we look at this from the other point of view, moment about the y-axis, of course, we want whatever our mass is to rotate about the y-axis. And so to do that, I would have to have a force going in this direction to do that. And again, my mass m sub I would be working to come out of the page to rotate. But, and actually I have this drawn the wrong way. Let me fix this. And so this would rotate about the y-axis this way, okay? It could be the other way, but just to keep it general convention, I'm going to have it spin clockwise here, okay? All right, so our goal here is to basically deal with the rotation about the x-axis and the rotation about the y-axis simultaneously, okay? But if you get this general idea of what a moment is from the visual that I've given there, you pretty much have what you need, okay? Now, let's move down to figure D here for a second. And what figure D is trying to do is show you that this center of mass that we're going to have, and I'm going to put it in green here, this center of mass is actually going to be located at the place where the two balance lines are going to intersect. And if we think about it, the balance lines is just going to be the balance line according to the y-axis, but well, that's going to be parallel to the y-axis, and the line that's going to be parallel to the x-axis that goes to the center of mass. In the part 1 video, we talked about how to calculate the moment for a one-dimensional figure. And essentially all we're doing with these balance lines is we're saying, hey, if I want to figure out what the moment about the x-axis is, or the moment about the y-axis is, oh, sorry, the center of mass about the x-axis and the y-axis, if I looked at the moment about the x-axis separately, and I looked at the moment about the y-axis separately, then what I would have is the vertical balance line and the horizontal balance line, respectively. Okay, where the vertical line, x is equal to x bar, that would be the one that actually spins about the x-axis, or rotates about there, about the x-axis. And of course, this other one here, which I know I have it on its side here, but we'll consider it to be horizontal here. This will be the one that will spin about the y-axis. Okay. And so again, all we're really trying to do is just kind of put those two things together simultaneously. And the best way for us to put it together simultaneously is actually to deal with it separately. Okay. And so that's what we're going to look at next here. So now that we kind of have a better idea of what this moment looks like in a two-dimensional case here, we see that the moment of this particular system about the x-axis, or the system moment, I should say, is just going to be the sum of all the little small moments for each mass m sub I that I have. If I do the same thing for the system moment about the y-axis, same kind of thing. And thus the x and y coordinate of the center of mass can be found the same way that we found it with the one-dimensional one. Okay. Of course, for the one-dimensional one, kind of looks the same. The numerator here is just the system moment. And of course, the system moment was just the sum of the product of the masses times how far each mass was from the origin. And that's divided by the system mass, which is going to be the sum of all the masses. And again, we haven't talked about the whole notion of dividing up the fin rod into pieces and changing the m sub I to the delta m sub I. We're not going to deal with that now because we kind of know where that's going. Okay. So the main thing here is to know that we have these two formulas here, and let me erase this. We'll try to erase it. So we have these two formulas here that look very similar to what we were doing in the one-dimensional case. And we know that if we allow n to approach infinity, we're eventually going to be dealing with, integrals again, okay? So to sort of round this out here, let's look at a 2D figure, I guess a two-dimensional figure where the mass under consideration here is a thin flat plate with negligible thickness, okay? And so the main thing here is that if we can assume that our mass is distributed like a continuous function, okay? So in other words, we don't have like all mass in one place and then, there's nothing, and then there's some more mass and there's nothing. If we can basically model the mass for this 2D figure like a continuous function, then that is the avenue that opens up for us to be able to now use calculus, and in particular use integrals. So to make a long story short here, the way that we're going to go about trying to model this situation for a two-dimensional figure is that we're actually going to concentrate on trying to model a sample piece, or as we're going to call a strip of it, okay? And if you've been watching my videos, we did this sort of thing whenever we talked about modeling problems that had to deal with work as well, okay? So if you remember with work, we had to kind of look at everything and say, all right, well, what is this force and what is the distance? And once we model that for let's say for a slice of water that was in a tank or something, then we just said, all right, well, we got the general idea of what a slice of water in a tank is. If we have a infinite number of these and we add it up, then, we can figure out what the total work was to get the water out of the tank. So we're going to use a similar approach here by saying that if we want to know the center of mass for this whole entire figure, and let's say I assume that the center of mass for the entire figure is here. I'm going to call that X bar or Y bar. Then what we're going to do is take a sample of that 2D figure, and we're going to find the center of mass for it. And we're going to call the center of mass for that sample X tilde Y tilde. And so if we can model the center of mass for X tilde Y tilde, and we can add a bunch of those up, then of course what we'll actually have is the actual system mass for the entire 2D figure. Okay. So here, just as we cut the one-dimensional figure or the thin rod model into small pieces, we'll now go ahead and cut our 2D figure into small strips. Okay. And so, again, strips, because our strips are two-dimensional. They will have a length and they'll have a width. So you can choose to cut these strips in a horizontal or vertical fashion. And that's important because depending upon how your plate, your thin plate is defined, sometimes it may be easier for you to model your situation with horizontal strips. Other times it may be easy to do it with vertical strips. And so in some of the examples that we'll do, I'll show you what that actually looks like when we do it one way versus another. Now, without loss of generality here, I'm just going to look at the vertical case only because I've drawn this particular figure here in figure E with a vertical strip. Okay. So in looking at that, we know that the center of mass for this sample strip is going to be the X tilde Y tilde point again. The mass of the strip will be delta M. And so now we're, putting in the particulars there, because again, we know that our mass can be modeled throughout the figure as a continuous function. So we can't assume that it's going to be the same thing. So that's why we're going to call it big delta M here. And the moment of the strip about the X and Y axes are going to be delta M Y tilde and delta M X tilde respectively. And that's for the same reasons why on the other page here, we talked about the moment about the X axis was M sub I, Y sub I, and the moment about the Y axis is M sub I, X sub I. Okay. Same kind of thing here. Okay. Now, if you need the visual, I'll go ahead and draw that. So if we're doing a moment about the X axis, then we see this, what I'm going to call a force here is going to be acting on this mass, and that's going to make this spin like this mass is coming out of the page towards you and spinning about the X axis. Okay. And of course, if we have it the other way, if it's coming from the Y axis, then of course, we are assuming that our mass is rotating here about the Y axis. And that's where that moment comes from. So if we are able to say all that, then of course, we know that X bar, which is going to be the X coordinate for the center of mass, is just going to be center system moment divided by system mass. Instead of it being just a regular X value or X bar in this case, I'm sorry, not X bar, but just a regular X value, it's just going to be X tilde here. And of course, our mass is just delta M sub I. And for Y bar, which now we're considering the moment about the Y axis, we would consider Y tilde. Now, again, if you're wondering why I'm using X tilde and Y tilde now, if we go back to what we saw earlier here, remember that the X coordinate and Y coordinate system center of mass, we had this X sub I here, and we had this Y sub I here. Okay. And we were talking about a particular mass at a particular location on the plate, and this X sub I is a particular distance X from the origin, and this Y sub I is a particular distance Y from the origin. Okay. And so all we're doing now is replacing the x sub I and the y sub I with the particular point x tilde y tilde. Okay. And so we have the x tilde I on it because of the fact that we're only talking about this one vertical strip here. And we're going to have a whole bunch of vertical strips to model. But we're going to basically take this general model that we're going to have and add up all the strips. Okay. So with that being said, again, if we let the number of strips n approach infinity, then we are cutting these strips into smaller and smaller pieces. And as a result, our summation signs in the aforementioned formulas would change to integrals. And so this is how this turns into us actually being able to have integrals here. Okay. And so now that we see this, we know that we have a nice standard way to come up with the x coordinate and y coordinate for our center of mass for a two-dimensional figure or like a thin plate. So to summarize, and this is the part that's important to you. So if you've kind of been waiting to say, hey, well, what is it that I really need to know here in these videos? What I'm showing you right now is what you need to know. Okay. So we know that the moment about the x-axis here is going to be the integral of y tilde dm. And I'll define what the dm is a little bit later. Our moment about the y-axis is going to be integral of x tilde dm. And our system mass is going to be the integral of dm. And so the important thing here, as you can see, is that we have to figure out what this dm is. Okay. So if we go down here for vertical strips, notice here that our x tilde is going to be just the same as x. Okay. And I'm going to explain why that is. So I'm going to go back to the drawing that I had earlier here. So when we have a vertical strip like how you see here, notice that this distance from the origin to here is an x value, but the x value is x tilde. Okay. So we know that for this particular vertical strip here, its center of mass is going to be exactly at x tilde. Okay. Now, of course, what y tilde is, we're going to deal with that in a second. Okay. But the main thing here is that whenever we have vertical strips, the x coordinate for the center of mass is always going to be x tilde. Okay. If we have horizontal strips, then just the opposite is true. We're going to have our y coordinate for the center of mass be y tilde. Okay. All right. So let's jump back to that summary area. All right. And so I'm going to change colors here just to have some kind of contrast. So again, for the vertical strips here, we know that x tilde is just going to be an x value. Our y tilde is going to be exactly 1/2 of whatever our function is here. And I have circles around that because of the fact that depending upon the situation that we are referring to, that may change. Okay. Now, we need to figure out what this dm is. And what dm is essentially it's going to be the density of the object that we're dealing with times the differential area. And how we can get the differential area, we know that area of the strip is just going to be length times width. Okay. Well, we know the length of the strip, and this assumption here, and I'm going to draw this. Let me go here. So the assumption here is that when we are talking about the strip, let's say we have some function that looks like this, and we're starting at this x value and stopping at that one. and let's say our plate is going to look like this figure from here to here to here to there. So all that's in between here is going to be what the plate looks like. In this case, we are considering the length of the plate to be whatever the length of f of x is with respect to the x-axis, okay? And so, of course, if we had a strip here, I'm going to go ahead and draw one. Let's say if we had a vertical strip here, then, of course, the center of mass for the strip should be exactly halfway of the length of that particular function with respect to the x-axis, okay? So that's pretty much all I'm saying, okay? Now, again, we're trying to characterize this strip, and we know that this strip would have to have a length here of f of x, if, of course, what we're talking about down here is the x-axis. The width of the strip here would just be the change in x values, and so it would normally be delta x here, but as delta x is approaching 0, that's actually going to be the differential dx here. So that's what we would put here. And of course, this is a length, this is a width. So if we multiply the dx and the f of x here, that would give us the area of this strip. And what we're going to call the area of that strip is dA. So it's essentially just going to be f of x times dx, okay? So if we go ahead and switch back here, you'll see that length of the strip is f of x, width of the strip is dx, and area of the strip would be dA, which is just going to be length times width, which is just going to be f of x times dx. And again, this is only when the height of the plate, the height of the plate in this instance, when we're using those vertical strips, is defined as the height of the function with respect to the x-axis, okay? Now, if we use horizontal strips, then everything would be the opposite. Instead of x tilde being x, y tilde would be just a y value, okay? Here, we know that since y is just going to be equal to y tilde, then x is going to be 1/2 of the height of the function with respect to the y-axis there, okay? Again, we need to know what dm is, and dm is just going to be the density times this area, or differential area, and the differential area is just going to be the area of the strip itself, which is going to be length times width, which in this case is going to be f of y times d of y, okay, or dy. Now, I have another page I want to show you just to make sure that this is really, really clear before we start doing examples, because once we start doing examples, we're going to do a lot of them, okay, so that you can get a good range of how we use this stuff. So on the next page here, so note when modeling the centroid or center of mass for a single vertical or horizontal strip or plate, please note that in general here, that your y tilde is going to be the height of the plate divided by 2, which is going to be some function of x, okay? And x tilde is going to be the height of the plate divided by 2. It's going to be a function of y, and that's for horizontal strips. Now, this y tilde is modeled such that if it is modeled halfway between the height of the plate, okay? So usually displacement is halfway between the given function and the x-axis, like I said before, but this is not always the case, okay? And we're actually going to see when we go a little bit later in these videos, probably in part 3, when we start to talk about finding the center of mass of a thin plate bounded by 2 curves, we're going to see that. I'm actually going to skip to that here for just a second so that you can see what I'm talking about. but we'll talk about finding the center of mass of a thin plate bounded by two curves here in just a second. In the next video. So X tilde is modeled such that it is halfway in between the height of the plate. Again, and usually this placement is halfway in between the given function f of y and the y-axis. But again, this is not always the case. And so one example of this, and I'm going to pause the video for a second and go back to it. You're going to see one example, and then I'm going to show you another one just so that it's clear. Now, if we go back to this figure E here that we had earlier, if I looked at, let's say from here to here, if I was to kind of trace this like that, then we could consider this blue curve here to be a function. Okay. Now, let's say I have this in green, and I'll do here, and I trace this down here this way, then this green curve could also be a function. And so here I could look at this as my function f of 2, f sub 2, and I could look at my blue function as f sub 1. Okay, and in this case, I know that the length of this particular vertical strip would just be the difference in between f of 1 and f of 2, because that would actually be the difference of them. If I wanted to get halfway in between here, from a y value perspective, I would actually have to do f of 1 plus f of 2 divided by 2. Okay? And so, of course, that's because if I did f of 1 minus f of 2, I would just have this length here. But just in looking at that, f of 1 minus f of 2 would actually put me at about here. And then if I took half of that, that would put me about here. Okay? So what we want is f of 1, which is this total length from down here up here, and then f of 2, which is a little bit more, and then we want half of that, which would get us down here. Okay, so those are like the small little nuances that we have to pay attention to whenever we are modeling these situations here to find the center of mass, both for the x coordinate and the y coordinate for it. Okay. Now, later on in this set of notes that I'm making videos on, you'll see that figure F here is another example of that. So we see that we have a vertical strip here, and we have our function f of x, and we have our function g of x, and this plate here is going to be on the top and bottom is going to be modeled by this function f of x. And if we look at the strip here, we are going to have to make sure that we say that the actual length of the strip is actually going to be the difference in between f and g. Okay. And notice here that the y coordinate for the center of mass is going to be the sum of f and g, but divided by 2 or multiplied by 1/2. Okay. So that's what I was talking about earlier when I was saying that, hey, that summary that I gave you isn't always true. That's only in the case whenever we're talking about the function is defining the height of the plate with respect to the x-axis. All right, so for our first example here, I already have this one worked out just to kind of give you a sense of how these problems go. I also have this one worked out because we're actually going to take this problem and do it again, but we're going to do it with horizontal strips instead of vertical strips so that you can see the similarities and differences on how we work a problem like this and yet still get the same answer. Okay, so we want to find the centroid, which is short for center of mass, of a triangular plate bounded by the lines y equals 0, y equals 3x, and x equals 2, where the plate has uniform density of 3 grams per square centimeter. Okay, so in this case, since we know that the density is uniform, we really can ignore it. I don't ignore it in my problem, but you're going to see that eventually the density is going to basically reduce itself to 1 with something else. Okay. All right. So we're going to use vertical sample strips to model this system. So our solution here is that since this thin plate is bounded above by y equals 3x, and notice that you do need to know how to be able to graph these types of relations from memory. Of course, y equals 0 is the x-axis. Y equals 3x is just a line with a slope of positive 3 going through the origin. And x equals 2 is a vertical line. Okay. And so you're going to have to be able to do that. So from here, we see we have our vertical strip here. So we just need to figure out what our x tilde and our y tilde is going to be. We easily know, because this is a vertical strip, that our x coordinate for x tilde is just going to be x. Okay, that's going to be real simple. For our y coordinate for the centroid for this sample is going to be halfway in between the actual height of the function here. So it's just going to be half of 3x here. And we say that because everything is with respect to the x-axis here. Okay. And then, of course, we know that the width of the strip, if we can get it as small as it can, is going to be dx. The height of the strip itself is going to be f of x, which is the actual height of this function, y equals 3x itself. And then, of course, from that, we can put that all together and figure out, of course, that dm is just going to be the density times the differential area. And that differential area is just going to be the length of the strip, which is just going to be this 3x here. And the width of the strip, that is going to be dx. Okay. And all that works here because we know that the moment about the x-axis is just going to be the integral of y tilde dm. Moment about the y is going to be integral of x tilde dm. And the system mass itself is just going to be integral dm. Okay. And I've purposely not put the limits of integration on there yet because we will deal with that when it's time to actually do it. But here, since we're doing vertical strips, that it will be from 0 to 2. Okay. So again, if we look center of mass, we know that x tilde is just going to be random x value here. We know that y tilde is going to be exactly 1/2 of that function y equals 3x. The length of our strip is going to be the actual height of the function, which is 3x, since the plate is bounded below by the x-axis. The width of the strip, as we discussed before, is dx. So that means that the differential area here is just going to be 3x times dx. And since our density is uniform, we could ignore it, but I'm just going to keep it in the problem here, multiply all that times 3. So now that we have that all in place, it is really just a matter of putting all of our information into these 3 formulas here and going to work. Okay. So we see here that the moment about x is going to be the integral of y tilde dm, of course, going from 0 to 2. Y tilde is actually half the distance of the function from the x-axis. And dm is going to be 9x dx. And so from there, factor out all of our constants, take the antiderivative of what's left in the integrand, and then from there, figure out what our answer is. And this is going to be 36 gram centimeters. Okay. So again, that's our moment. If we do the same thing for the moment about y, we use x tilde dm. If you remember, x tilde for vertical strips is just x. Our dm, of course, is 9x dx. And then from there, looks like simple integration, where we factor out the 9, take the antiderivative of x squared, which is going to be x cubed over 3, and then evaluate that from 0 to 2, and we see that we get 24 gram centimeters. Okay. Now for our system mass, we just integrate dm from 0 to 2, and of course dm is just 9x dx. Factor out the 9 here and just take the antiderivative of x, which is just x squared over 2. Figure all that out, and we see that we get 18 grams. Okay. And notice for the system mass, we don't have grams times centimeters because the mass is just that. And of course, we just keep it as grams. Whereas the moment, that is the product of mass times distance. Okay. And so now that we have all that information here, we remember that x bar, which is the x coordinate for the centroid for the entire plate, is just going to be the moment about y divided by m. The y coordinate for the centroid, or the center of mass for our plate, is just going to be the moment about x divided by m. Okay? And you see we have all the numbers that we need here. So if we take 36 divided by 24, if we take 36 and divide it by 18, that gives us the y coordinate. And if we take 24 and divide it by 18, we're going to have the x coordinate here. Okay. All right. So to conclude this video, I'm going to do this same example, but I'm going to do this example using horizontal strips instead of vertical strips so that you can see how this works. All right, so we have the same example now, but the only thing that's different is we're going to use horizontal strips. So we know that the formulas stay pretty much the same. So the moment about x is going to be the integral of y tilde dm. And this is going to go, well, I'll handle that part later. So the moment about y is going to be integral of x tilde dm. And the system mass is going to be integral of dm. Okay. So now the thing is how do we actually characterize what our x tilde, y tilde, and dm is going to be? Okay. So let's talk about that. So let's do x tilde and y tilde here. Okay. All right, so I have a picture of the same problem that we had before, visualizing it. But now what I'm going to do is I'm going to make a horizontal strip instead of a vertical one. Okay. And so if we're looking at this, we know that our x tilde here and our y tilde, if you remember, for vertical strips, it was x tilde that was just the normal x value. So that means now that we have a horizontal strip, it should be our y tilde just should be a random y value. Okay. Now, in order for us to figure out what x tilde is going to be, we know it's going to have to be 1/2 of, and then some function of y. But the thing is, we need to know what that function of y is. Okay. Now, if we're looking at this in terms of a function of y, what we would actually have to do is flip this graph here so that it would look something like this. Okay. So this would be x equals 2 here, and what we would have is y equals 3x, kind of looking like this. Okay. And of course, if we flip it, it would no longer be y equals 3x. It would be more like x is equal to 1/3 y. So I'll go ahead and switch that now. Okay. So now what we know is that here this plate is being bounded by what was the x-axis here. It still is, but of course it's going like this now. Okay. So it's bounded in between here, here, and there. Okay. Now, if I go ahead and draw my horizontal strip now, which is now going to be vertical if I draw it like this, it's going to look like this now. Then notice that the height of this particular strip here, or the length of the strip rather, I should say, is going to be the difference in between x equals 2 and this function here. Okay. And so my x tilde should be halfway in between that. Okay. So what I want is the halfway point of this plate here. So to do that, what I would have to do is I would actually have to add x equals 2 and x equals y divided by 3 together, and then take half of that in order to actually get halfway in between here. Okay. Because remember, if I say 2 minus this, I would be here, and then half of that would be way down here somewhere. Okay. But I want 2 plus the y divided by 3, and then after that get halfway, which will get me where I want to be at. So all of that to say here that this x tilde is going to be 1/2 of 2 plus y divided by 3. And then of course that's multiplied by 1/2 to get to that x coordinate there. Okay. And so in the grand scheme of looking at things, this is kind of like where your x tilde would be for this, and your y tilde would be here. And of course, that would just be equal to y. And so that's how we would actually model. So that's how we would actually model the x tilde and the y tilde. Okay. Now, everything else is relatively easy here because, again, with all of our situations, for the moment about the y, moment about the x, we need to figure out what this dm is. And dm is just going to be the density times the differential area. And the differential area is just going to be the length of your strip times the width of your strip. So I'm just going to say length times width. And we'll put strip for both of these. Okay. So if we look at this, and actually we'll go back here now. So the width of the strip here would actually be dy. Okay. Let's say length of strip, width of strip. All right, so we know that the width of the strip here is going to be this dy. And we know that the length of the strip here is just going to be the difference in between these two functions here. So it's going to be 2 minus y divided by 3. Okay. And so now that we have that, we know that the differential area is just going to be the product of these two, which would just be 2 minus y divided by 3 dy. And thus dm is going to be this delta here times all this business. Okay. And so we can use that dm for our moment about the x, moment about the y, and for our system mass. And so that is what we'll use to finish out this problem. All right, so from this point here, we have everything that we need. And so I just copied over what I had from the other blank page that I was working on. So now all we need to do is figure out what the moment about the x, moment about the y, and moment about or the system mass is going to be. And of course, once we have all that, then we know that x bar is just going to be the moment about the y divided by the system mass, and y bar is going to be the moment about the x divided by the system mass. So therefore, if I take the moment about x, that's going to be integral of y tilde dm. And so now we need to identify where what the limits of integration are going to be. All right, so if we are trying to figure out what our limits of integration are, remember that for when we did the vertical strips, it was from 0 to 2 here. But now, since we are integrated with respect to y, this should be from 0 to 6, okay? So that's what that's going to be. So we're going to say from 0 to 6. And of course, our y tilde is just going to be y. And our dm is just going to be that density 2 minus y divided by 3 dy. And we'll do it like this here. And then, of course, we just integrate that. So, all right, so from here, we'll go ahead and integrate that. But before I do that, we want to recall here that, I'm going to switch colors here for a second, that this value here, the density is 3 grams per cubic centimeter. Square centimeter, because we have that here. So I'm actually going to implement that into the problem now to make life a little bit easier for us math-wise. So if we do that, then this will be integral from 0 to 6. And if we multiply the 3 times both of those terms there, this will just give me 6 minus y dy, okay? And so now all I have to do is just take the antiderivative of 6 and y, which is, kind of easy. But here I have this extra y here, so I need to make sure that I have that. So this will end up being 6y minus y squared that I actually need to take the antiderivative of. And so when I do that, I know that the antiderivative of y is going to be y squared divided by 2. Of course, I'm ignoring the 6 there. And the antiderivative of y squared is u cubed divided by 3. And we evaluate that from 0 to 6. So that just ends up being 3y squared minus 1/3 y cubed. Evaluate that from 0 to 6. And now we just plug in 6 everywhere we see y. Minus, and we plug in 0 everywhere we see y. And of course, for both terms, that'll just end up being 0. And so all we have to do now is deal with what we have left. So we know that 6 squared is 36. And if we take 36 and we multiply that times 3, we should get 108. So that's going to be 108 here. And of course, 6 cubed, I'm just going to kind of work that down here. 6 cubed divided by 3. We know 6 divided by 3 is 2. And so we got 6 times 6, which is 36, times 2, which is 72. So we'll have that. And of course, the difference in between 108 and 72 is going to be 36. And so that will be what our moment about the x-axis will be. And of course, the units for that, if I wanted to put those units on there, we would have gram centimeters, okay? So that would be 36 gram centimeters. So now we need to do the same thing for the moment about the y. And here we know that this will be integral from 0 to 6 of x tilde dm. And if you remember, our x tilde is going to be 1/2 of 2 times y divided by 3. And if I was to actually go in and multiply that through, that would be 1 plus y divided by 6. So I'm going to go ahead and implement that now. So the x tilde is just going to be 1 plus 1/6y multiplied times dm. And that dm is going to be density, which we've already said that it's 3, so I'm just going to go ahead and implement it there. And I'll just write this here. So we said that that was 3, and this is going to be 6 minus y dy. And so this dm will be 6 minus y and dy there, okay? And of course, now we're going to have to multiply those two binomials. So 1 times 6 is 6. 1 times a negative y is minus y. 6 times y divided by 6 is just y. And then y divided by 6 times a negative y is going to be a negative y squared over 6. All that times dy. You see here that the minus y and the plus y cancel to 0. And what we have left is just this 6 minus y squared over 6. And that is what we actually need to take the antiderivative of. All right, so from here, let's go ahead and drag this over. And we'll see from here that we'll just have the antiderivative of 6 will just be 6y. And we'll do the minus 1/6 here. Antiderivative of y squared is just y cubed over 3. And that'll be evaluated from 0 to 6. So for our first term, we'll have 6 times 6, which is 36, minus 1/6 times 6 cubed divided by 3. And minus, of course, for both terms, if we plug in a 0 for y, that will just be 0. And here we know that 6 cubed divided by 6 raised to the 1 is just going to be 6 raised to the 2, which is 36. And all that is 36. And 36 divided by 3 is 12. And so all we have is 36 divided by 36 minus 12, and that gives us 24. Okay. And last but not least, the system mass will be integral from 0 to 6 of dm. And of course, this dm is no different than the dm that we had before. So if we go to over here, this is going to be the same dm here. So the same value that we got for that whenever we integrated it out, which was going to be 18 grams, we're going to use the same thing. So so I'll go back here. It'll end up being the same thing, even though I have something different here. Okay. So here, this will be 0, 6. This will be 6 minus y dy here. And of course, this will be 6y minus y squared over 2. And that will be from 0 to 6 there. And then, of course, we just plug in 6 in the first term. So 6 times 6 will end up being 36 minus 6 squared over 2. And then minus, whenever we plug in 0, it's going to be 0 for everything. And we'll have 36 minus 6 squared is 36. 36 divided by 2 is 18. And we see that we still end up getting 18. Okay. And again, this is in grams. And these other two here is gram centimeter and gram centimeter. Okay. And so now to finish up, we know the moment about we know that the x coordinate for the centroid is going to be the moment about the y divided by system mass. And the moment about the y, we found that that was 24 divided by system mass is 18. And of course here, this would be the same as 12 divided by 9, or divided by 3, 4 divided by 3. Okay. And of course, this would be, the units here would be centimeters. So this is actually a length. And of course, y bar would be the moment about the x divided by system mass. And this would be 36 divided by 18, which would be 2 centimeters. And thus the centroid would be 4/3 2 at that particular location there. All right, so this is an example of how you see we can model a two-dimensional figure, and you can see how we model with vertical strips as well as with horizontal strips. Okay. Now, the part 3 video that I'm going to do is we're going to do more examples, but with these examples, you're going to see that some I'm going to use with horizontal strips, others I'm going to use with vertical. But the main thing here is that I'm going to have all of these worked out because, again, these problems can get a little long. But now that you kind of know how to model them, the key here is just to make sure that you model the height of the actual strip correctly, and model the x and y coordinates for the centroid of the strip correctly, and everything else kind of just comes relatively easy once you do that part right. So I'll see you in the part 3 video where we're going to cover more examples doing the 2D cases. I'll see you there.